Rising liquid in a pipe. Two very large open tanks, very large open tanks, A and F, contain the same liquid. A horizontal pipe, BCD, having a constriction at C and open to the air at D, leads out of the bottom of the tank A. And the vertical pipe E opens into the constriction at C and dips into the liquid in tank F. Assume streamline flow and no viscosity. If the cross-sectional area at C, so we're assuming no viscosity, therefore energy conservation. If the cross-sectional area at C is 1/2 the area at D, cross-sectional is 1/2, and D is a distance h1 below the level of the liquid in A, as you can see in the figure, to what height h2 will the liquid rise in pipe E? Express your answer in terms of h1. Okay, so these are very large open tanks, atmospheric pressure outside. We have an opening at the bottom of tank A, so through B we have a fluid flow, and it goes through a constriction C, and then it goes through the pipe D, which is a distance h1 below the surface of A. Now, because you have flow here, according to Bernoulli's equation, this will cause a decrease in the pressure on this pipe, and therefore this liquid level will rise here in order to account for this. And this is basically the mechanism similar to the perfume bottle. When you blow air through this tube, you get to see a decrease in the pressure and the fluid comes out as a result. So it's the same principle as the perfume bottle. Okay, so I start with the Bernoulli equation for the surface of A and D. So between A and D, let's write Bernoulli's equation. So at the surface of A, I have the atmospheric pressure P0. And with respect to D, I have a potential energy rho GH1. And then the surface of A is coming down with a certain speed, 1/2 rho VA square. And this is equal to the outside pressure at D plus 1/2 rho VD square, the kinetic energy term for the liquid flowing through pipe D. Now you can see that these P0s will cancel, and at the same time I have the continuity of the fluid flow, which tells me that the area at A multiplied by the speed at A is equal to the area at D multiplied by the speed at D. So that's the volume flow rate. And since A is a very large tank, the area is much greater. Area of A is much greater than the area of D. I'm going to see that VA is negligible compared to VD. All right, so therefore I'm going to neglect this term here. So what does that tell me? So this tells me that the fluid speed at D is square root of 2gh1. Why? Because these rows will cancel as well. So it's going to be square root 2gh1. Now the area of constriction C is half of the area of the pipe D. So again, the continuity of the flow, AD times VD is equal to AC times VC. The volume flow rate is the same. So AD times square root 2gh1 must be equal to AC, which is AD over 2, multiplied by VC. So this tells me that VC should be equal to square root of 8GH1. All right, so this 2 goes as 4 inside, so it makes it square root 28GH1. Now, what is the gauge pressure at C, surface of E, which is responsible for the rise of this liquid? So let's write Bernoulli's equation between A and C. The pressure at A is P0. I have 1 over 2 rho VA square, kinetic energy term, plus rho GH1. All right. So I neglect the difference between these two. So it's almost H1 here. And this is going to be the pressure at C plus 1 over 2 rho VC squared. Once again, since A is a very large tank, I neglect the speed at A. So this goes away. And I find that the gauge pressure at C, PC minus P0, is equal to rho GH1 minus 1/2 rho VC squared, which is 1 over 2 rho VC squared is 8GH1, because VC was square root 8GH1. So this makes this a 4, and therefore I obtain the gauge pressure PC minus P0 to be minus 3 rho GH1. Remember, it's the same liquid in all the tanks. All right. So knowing the gauge pressure here, I'm going to write Bernoulli's equation between E and F. So let's work on that. The pressure at the surface of E, which is the pressure at C, plus rho GH2, potential energy, is equal to the atmospheric pressure P0. So we reach equilibrium, nothing is moving anymore, and we have the equilibrium height, right? So we only have potential energy term here. And this gives me pressure at point E, which is the pressure at point C, is P0 minus 3 rho G H1 plus rho GH2 is equal to P0. So P0s disappear. And this tells me that H2 is 3 times H1. All right. So we have the following configuration: 2 very large open tanks open to atmosphere. We have a fluid flow from A towards B, constriction C towards pipe D, which has twice the cross-sectional area of C. So C is a constriction. And D is located at a distance H1 with respect to the top surface. Well, you can see that this H1 is basically should be defined with respect to the center of D here. So that would be the same as center of C. So C is also at a distance H1 approximately. And because of this flow here, the pressure, gauge pressure at the pipe E decreases and causes the liquid to rise from the open tank F towards the pipe E. Okay, so what is this equilibrium height? First, I applied Bernoulli's equation between pipes, the tank A and pipe D. The pressure, outside pressure, P0 here, outside pressure is also here. So P0, P0 on two sides. I have a potential energy with respect to D, rho GH1. And then this flow, because of this flow, this top surface is coming down. So it is 1/2 rho VA squared. And because of this flow here, I have a kinetic energy term 1/2 rho VD squared. And because the area of the tank A is very large, I can neglect the speed with which this top surface is coming down. So VA is neglected, and I obtain VD equals square root 2GH1. And knowing the volume flow rate must be the same between D and C, and the area of C is half of area of D, I obtain Vc to be square root 8gh1. The gauge pressure at C, which is the same thing as gauge pressure at E, can be obtained using Bernoulli's equation between A and C. The pressure P0, 1/2 rho VA square, which is again very small because it's coming down very slowly, plus rho GH1, the potential energy, is pressure at C plus 1/2 rho VC square. So that's the rate at which the liquid is flowing through C. And this is going to give me a gauge pressure of minus 8 rho GH1, substituting for VC 8GH square root 8GH1 to this equation. And then I wrote Bernoulli's equation between E and F, the pipe E and tank F. I have the gauge pressure here, PC or PE, which is minus P0 minus 3 rho GH1. Then I have the potential energy term, rho GH2. Here I have outside pressure P0. This is at equilibrium, no motion on tank F. So P0s cancel and I find H2 to be 3H1.